So here it is. So as I told you, the first couple of classes, we want to spend some time on, I call it basic digital signal processing, because signal processing is a grad course of its own. So there is no way we can cover it in a couple of classes, but I do my best. So these are the topics that I identified as important for the topics of this class. So first, talking about signals. We have a mix of students. Some of you have never worked with a signal. Some of you are working with signals every day. And then what are amplitudes, phase, envelope, and very important, we go towards talking about Fourier transform, fast Fourier transform, and then time frequency analysis, noise, filtering. Depending on how fast we go, I may leave cross-correlation for later on when we actually go to velocity measurements. Let's see how fast we go. Okay, so why do we bother with signal processing? If anyone doesn't have handouts, these are here. So last time I showed you schematically what a very simple acoustic or ultrasonic test looks like. And when we have one emitter here and one receiver, we send in, we generate a pulse. Let's say it may look like that, and we receive it on the other end. What we receive on the other end is actually looks something like that. So you are measuring something with time. This we call a signal. I asked you if you could actually download the files. Did everyone download the files? Those are LabVIEW binary files. So to open them, we can't simply click on them or use Excel or anything like that. We need to use some MATLAB commands. Do you want to try to see if you can open them? So first you have to open them. It's you want to read it. So that's R is for read, B is for binary. And then you actually read the file that you opened in FID. You have this in your handout, so try to see if you can open the files. So you don't have the So here, when you read it, this is the size. And that's the precision of the data. I don't know how it is in Python. Different. But you can open it. If you have difficulties, I also uploaded the math files, so you can just click on it. But you should be able to open any kind of file. And in my lab, because we use LabVIEW, most of the files that we collect, almost all of them are not ASCII, they are binary. So that's the kind of way that we use to open them. If you open and plot the first 10,000 points of either file in contact or the velocity file, you are going to see these signals. Not the information file, you need to open the data file. If you have difficulty, just open the math files and plot the signals, especially if you have never done that.
Which file?
The math So one is in contact. That's this signal. If you plot the first 10,000 points, you will see this, and this is the other one, velocity.
I can't even open the text file. It opens in the binary. The actual MATLAB file. Like when I try to open it in a like notepad.
Open it.
I mean, when I downloaded the folder from Canvas and unzipped it, the files didn't work. But when I downloaded them individually,
So like
they
this.
did work.
Oh, okay.
So let's see.
I don't know why.
Let me see if that works. I was wondering what's going on.
Do you have one for that?
Yeah.
So Clay is saying that you need to download the files individually for them to work. So all we need to do is to download the DAT files or the math files. You don't need the info files. Yes, just plot the first 10,000 points.
So I've got the mat files open, but I'm trying to read the data files as specified.
Yeah.
It doesn't seem to be working.
No, this is not how it is. So this is just, you are opening it. You need to define a variable here called data to read it.
Oh, okay. Rather than outlining it.
Yeah.
No, you need to have both of them. So if you are not familiar with MATLAB, which looks like, you need to really spend time on the basic commands. This is, you need to type both sentences. One is opening the file, this is an ID of the file, and the other one is reading the data in this file ID. That's one reason I wanted actually to see. So you can just plot the first points. You know how to finish the axis. Yeah. Wait, no worries. You can do it by commands too. Just click on x-axis. This is, you can just look to see, I think it's 20,000. Doesn't matter.
So this is what's giving me when I
That's the
downloaded
info file.
That's the oh in contact. And the rest of it is
Yeah.
So it's 110
I think that's-
megabytes.
Yeah. Yeah.
Yeah, that's what
So just look at, if you go to edit figure properties, you can choose the range for x and y axis. You can do this also via commands, but basically you can zoom in the data. For now, I just wanted you to see how a typical data looks like. Some of you have never seen one before. So that's what it is. So you have a column of numbers. Sometimes you also, with that, you save the time too. But I saved the information in an info file that you saw. All those numbers have some meanings. But we get to that a little bit later. I also have sent you and uploaded kind of a MATLAB cheat sheet that there are some comments in it. that could be helpful later on. Okay, so let's move on for now a little bit, and then we get back to that. So you have it. Yes, we have to plot it. I don't know the numbers, so I cannot tell you. Okay. So go to video. Video properties. That's very cool. X-axis. I don't know how to make Chinese, but it is good. If you just click on the X-axis, then you can change the limits. No, you have to a little bit drag it. No, not there. Those are tick marks. You can't control. Yes, thank you. You should just increase the size of it. Ryan, you okay? You know how to remember these files.
Yeah, I don't have it, but I can figure it out. I can just.
It's on canvas. Yeah.
Yeah, but I can't even open this text file to see what this code is. So that's weird.
Don't worry, it's not very critical. Especially for you, I know these basic things. But it's good to know how you would be able to open my files.
No, I'm gonna try and rewrite them. But I just like, this is what I get when I try and open the actual text file, like the
info file.
well, no, the map file, which is that's the code, right?
The map file is just saying
Oh, that's just me
M files are called. Map files are not
then. Okay, I was thinking that. So is that what it is?
Oh, no, this
That
is
is,
it's just that
I thought you were
once
opening
you
the dev.
plot it, you have to change your
Sorry.
XD. Let's move on. Okay. So, if this was the first time you plotted a signal, congratulations. Let's move to the Fourier transform. We get back to that. So, make sure that you can open this kind of file because, as I said in my lab, all the files look like that. This is a signal. So the signal is nothing else but a graphical representation of a quantity which is changing with time. Now, this quantity can be different things. For example, could you give me some examples of something that you measure maybe on a daily basis, something that varies? For example, on your smartphone. Is there something that you monitor over time?
Battery.
Battery? Okay. How much battery you are using? You monitor that day? Okay, data consumption if you have limited amount of data. Maybe some of you have those Fitbands. You track the number of steps you're taking. The temperature, that's maybe something that a lot of people are tracking, etc. So all of them could be a signal. So here, I'm showing something which may be familiar to some of you. Do you recognize this instrument? What is it? It's a seismogram. It's a seismometer. So what does it measure?
Motion of the Earth's crust.
The ground motion. What we can make it. So that's what it measures, the ground motion. If you plot the ground motion versus time, you're going to get a signal. In our kinds of testing, we use materials which are called piezoelectric ceramics. So what is a piezoelectric ceramic? Does anyone know?
Yeah, like quartz crystal.
What is it? What does it do? Why do we use that and we don't use rubber, for example?
It's a transducer, so one energy to another.
Which energy to what?
Electrical to means it's both ways.
Ex-
Electrical mechanical.
Exactly. So I've tried to show this here. Actually, this is now inside. This doesn't work, but you could have seen that if you apply mechanical stress to this kind of material, it changes that into electrical charge, and vice versa. So because of that, if you place it on a surface of a material which is vibrating, it actually gives you the voltage which would be proportional to the amount of displacement that it is experiencing, depending on the transducer. So typically what we get is a signal. What would be then the physical property that we are measuring? So here, seismometer is ground motion. What do we measure? Voltage. First we measure voltage, then we have to do calibration to change this voltage into something meaningful that we are looking for, let's say the displacement. So what we measure, what it gives us actually is just voltage. And it is versus time. Okay, so the signals can be periodic or can be non-periodic. If it is periodic, it is actually repeating itself. The non-periodic, it doesn't repeat itself. Let's see, with a periodic signal, we have a number of parameters which are important. One is the period of oscillation. How do we measure that? The distance in time between every 2 points that repeats itself is one period. It's very simple. If it is non-periodic, then basically the period is infinite because it never repeats itself. Correct? Now, a little bit more, let's say, important properties for later on. With each signal, we have a number of parameters that are associated with it. One is amplitude. How do we define amplitude? There are different ways to define amplitude, actually. Let's first focus on the red curve. So this is the signal we are now focusing on. So we can define the amplitude as what we call the peak amplitude. This is one amplitude. We can also define an amplitude which is from one peak to the other. We call it peak-to-peak amplitude. There is another amplitude which is very useful, and that is called RMS amplitude. Now I put here V, this could be also A, depending on the notation. What is RMS amplitude? RMS stands for root mean square. For example, for a sinusoidal, we can very easily calculate it. If we have just a sinusoidal, we have, so it is root mean square. So if we have a sinusoidal, let's say A sine omega t, that's a typical sine function. Let's say it's oscillating around 0, And then this is the sinusoidal, that's the angular frequency, and that's time. And the period is t. Let's say exactly the one that we see here. So if you want to calculate that, we can say the square. So we use, I just use that as the square root. That's how you have it in MATLAB. And then basically we take the signal, we square it, and divide it by the period. If we do that, the details, I have it in the notes that I already uploaded for you, but just in the interest of time, if you do that for a sine, we are going to get a over a square root of 2, which is about 0.707 a. So it's this much. Why is this a useful quantity? It's because the signal most of the time is not really at its amplitude. That's only at one point. So this is more like a better measure of the amplitude of the energy. So if you have a non-periodic signal, you can also calculate root mean square. The good news is in MATLAB, this is just one line. The function is called RMS, and you can get the RMS value of any signal you want. And it's a very useful quantity. What else? Another important thing that I want you to learn about signals is the concept of phase. So here, looking at the red one, what is the phase of the red signal? What does the phase mean? So let's step back a little bit and talk about the general formulation for one periodic signal. So I put here just A sine omega t. But typically, let's say amplitude sine omega t, we also have another term which determines pretty much where you start from. So you can see that the red sinusoidal starts from 0. So this was okay for that one. But the blue or the black, which is hard to see, they don't start from 0. They have some phase with respect to the red one. So basically, this red and blue are out of phase. If you want to compare that, for example, with these ones, they have different amplitudes, but if you look at them very closely, they all are in phase. Does this make sense to everyone? That means that they all start from 0 here. Compared to these ones, where you can see the red starts from 0, but the blue, it doesn't. So, if you, and now maybe you also see this dotted one, which is hard to see. Otherwise, do you see it in your printout a little bit? This one? Okay, so what about phase? If you continue this one, the blue, I delete the RMS here. is basically the time when this quantity, omega t plus phi, becomes 0. So that's t. So the time is actually, it's negative, you can see, and it's the phase over omega. Yeah. So the blue, you can think about it as being ahead of red. Yes? How much? By this much. It's ahead. The other one, the dotted one, which I hope you see a little bit here, is behind. So this one is behind by this much, which is, again, its phase divided by omega. So the dotted one is behind the blue, and the behind the red, and the blue one is ahead. What else I want to tell you about signals here? This omega t, I guess you all have heard about this omega somewhere at some point, but let's make sure. This is called angular frequency. What's the unit? Radian per second. A lot of times we don't work with omega actually. Most of the times we work with frequency, which is the unit is 1 over second or hertz. The period turns out to be 2 pi over omega. So 1 full circle is 2 pi. And what else? This is 1 over f. All for a periodic signal. So if we were to write the equations for these 3 lines, try to imagine the other one too. How would you write them? Let me write the easy one. The easy one is the red one. I write it here with red, and I said, okay, that one is, that's the peak amplitude in this case. Sine omega t, because the phase is 0. If I want to write the other two, so the blue one has the same amplitude, has the same frequency, you can kind of see, but it's ahead by some phase phi1. I think it was pi over 3. And I made this up. So it's ahead, plus. And if I write the black one, which you probably don't see very well, it has the same frequency, the same amplitude in this case. It's behind by 2 pi over 3. So a quick question. A cosine wave is ahead of a sine wave by how much? Pi over 2, that's it. Okay, this may be very elementary for some of you, but for completeness, I thought we should start here. So the periodic signals are very easy to show, because look, if I give you just the amplitude, frequency, and phase, I don't need to plot the whole thing for you. So if you have only 3 numbers, you can actually describe the signal completely. It turns out that the non-periodic signals are not as simple. So this is our non-periodic signal example. What do we do about that? Before going to the frequency domain and discussion about the transform, a couple of important useful things to know about non-periodic signals. Here, a lot of times it's helpful to get the envelope of a signal. You probably know this already. If you don't know, the way to do it is to look at the absolute value of Hilbert transform. Without going through, no, it doesn't write. That's interesting. So if you take the absolute value of Hilbert transform, it actually gives you the envelope that you see here. Okay, it writes again. What else I wanted to tell you here? Oh, I wanted to ask you if you can just show for yourself the peak amplitude, peak-to-peak amplitude, and what do you think the RMS amplitude would look like for this signal? Just draw it on your nose. Because it's not very clear, for example, why we need peak amplitude and peak-to-peak when you have a periodic signal. The thing is, most of our signals are not periodic, so you may have asymmetry between maximum and minimum. So a lot of times you want to take the peak-to-peak, divide it by 2, or just to take the peak-to-peak amplitude to be able to compare one signal to the other. RMS amplitude, you can just type RMS in MATLAB, put the name of your signal, and you're going to get an amplitude which is not as large as your maximum amplitude, but it kind of sums up the information in the rectified signal, kind of it would be somewhere here. So that would be a good exercise. And if you use these comments, you're going to get the envelope as you see here. Another important thing later on is this normalization. A lot of times we need to normalize the signals. For example, you want to normalize them with respect to the maximum value, minimum value, or you don't care, either one. So if you want to normalize it with respect to the maximum, you just divide it by the maximum value. You can divide it by the minimum, or you can divide it by the maximum absolute value to get that. Yeah. So, now, what do we do then with non-periodic signals? We just said that periodic is very efficient. If we have a signal, if we know the amplitude, if we know the frequency and the phase, basically we know everything we have to know about this signal. Right. I want to walk you through from here to developing Fourier transform without going into the mathematical details. So the first thing we have to talk about are Fourier series. Has everyone in the class at some point in his or her life heard about Fourier series? Right. So okay. Now, if I write this very simple notation that you are all very familiar with, if I expand it, it's just the things you know. And then I call A cosine phi. I call this B, and A sine phi, I call it A. So this is a periodic signal with the angular frequency omega. I can write it as A cosine omega t plus B sine omega t. And here the phase is not lost, it's just another way of writing it. So the phase, you probably have seen this notation before, it's actually, you can get it from the ratio of A to B. Now, if this is just one signal, a periodic signal could be a combination of a number of terms which look like that. So Fourier series representation is nothing else but having a number of sine and cosines at different frequencies summed up. Let me tell you what this is here. Here is 0. If I have a DC offset of A0, let's call this A0. DC offset means everything is together going up or down. And then at omega, now it looks very small, but this is actually one frequency omega. The blue is sine, the red is cosine. They are at the same frequency, but one is sine, the other is cosine, which is just pi over 2 ahead of the sine. At omega, and this is 2 omega, I could have made these kinds of figures for 3 omega, 4 omega, and so on. But this should give you the idea. So, the blue has, the amplitude is A1, here is A2, no, actually it's the red, let's see, that's the cosine. So the blue is the colors are, it's fine. The sine is B1 and B2. So if I sum these up, so you can imagine having a representation which looks like that. You have a DC offset, and then you go from n equal to 1 with took care of 0 here. So we start from 1. And then you have an cosine n omega t. So remember, this is at omega, this is at 2 omega, and then you can go to 3 omega, etc. down. Plus bn sine n omega t. So look where this is coming from. This is nothing else but just summing up a lot of different periodic signals. The fact that you have sine and cosine is because you have to take care of the phase if they are not in phase. There is nothing different. Very simple. It turns out that if we sum all of this up, we get something very useful, and that is nothing else but Fourier series. Now, why it is a good thing? Because you see, when you loaded your signals, you saw that this signal had 10,000 points. That's a lot of data. Now, if there is a way that we can just use these A and B's and A0 to represent a signal, which is not periodic, then it will be a more efficient representation. So we only have a handful of coefficients, and we can adequately then represent the signals with that. So that's kind of where the idea comes from. So it turns out that this guy, Fourier, he found out that this is not only good for periodic signals. If you have any kind of signal, you can write it as a sum of all of this, which was very useful. So now the question is, okay, where do we get then these coefficients? If we can write any signal, let's say we call it, we use my notes, I've used f of t and s of t, both here and there. So one is for signal, one is for function, doesn't matter. Function of time is a signal. So the idea is, okay, if this is really true, how can we get these coefficients? Without showing you exactly how, it's actually not very hard, but let's see how these coefficients are defined, because they are very, very simple. Now, A0, as you saw, is nothing else but the average of the signal. That's what it is. You saw it was just a DC component. So if the signal is not oscillating around 0, you have A0. If you have a nice signal which is just oscillating around 0, then you don't have any A0. So how do you get A0? You just average the signal. The average of a signal generally is you take the integral divided by the period. I write it like that for a reason. So this is nothing else but a DC offset. Or average. Now, AN and BN are also very easy to obtain. You just multiply both sides by sines and cosines, and since they're perpendicular, a lot of terms become 0. But the way it looks like is just that. So for AN cosine, what happened? For BN What happened? Okay. So, this number 1 and these cosines and sines, they together, they form an orthogonal basis. So what you are doing is actually going from one domain to the other domain. And these are showing how much of each component is actually contributing to the representation of the signal. So if we, let's say, imagine you would plot, here I keep omega, which is the angular frequency. If I plot here for omega 0, basically for the offset, it would be A0. For omega, if I plot a square root of A1 squared plus B1 squared, so this is omega. And then for 2 omega, I would plot A2 squared plus B2 squared, and so on. And this can go on. So they show how much of these components are actually contributing to the signal. If I had the original signal that I showed you, how would this look like here in this domain? It would be only one line, correct? So it would be very easy. But most signals, it's not as easy. So this one would be just one line. Just because I don't want to mix things up, I draw it here. It would be some amplitude. It won't be A, but something that you can get A from it. And it would be at omega 0. Then you know that you only have one frequency. But typically we have a number of different frequencies. Now, walking towards Fourier transform, we need to get away from the series, the way we saw it. So far, we kind of saw that it's possible to write every signal in this form. If we use Euler identity, the details are in the notes. I'm debating whether to write them down or not. But if you are not familiar with this, so if it is, this will be negative. So we want to go from here to Fourier transform. Now we have the series. We use some mathematical identities that you are familiar with, right? At some point, maybe not yesterday, but you have seen it at some point. Look up the details in the notes that I have uploaded, but we can write this whole thing in one single summation if we use the complex notation. So it all becomes a lot more similar to just that. And then this C sub n is then very similar to an and bn, a little bit different. You may say that, why do we need to look at the formulas? Because in a lot of papers you read, you may see these kinds of formulations. The Fourier transform is a very important thing, and in a lot of manipulations of signals, you may see the forms of Fourier transform showing up. That's why I think it's important to know where it is coming from. So pay attention to something very important here, and that's the sign of these exponentials. Look, what does it say? It says that we can write any signal as a summation of a large number of periodic functions. This is nothing else but a complex periodic function. And here is positive. And then the coefficients that are being used to represent the signal in frequency domain, they are obtained by this integral. And here this is negative. They go together in a way. Now, to make sure that everyone is following, let's just do a little example. I call this a rectangular pulse because that's what this is to me. That means here is time, let's say in seconds. I have a pre-trigger delay. Now you will understand what it means later on. So I have a delay in the beginning, and then there is a pulse. Of course, there is nothing here. The pulse is just there, and it's 100 millivolts, let's say. So it's a signal, but it's not periodic. And let's say goes from 1 to 4, which is too long, actually. Now the question is, how do we represent this in frequency domain? So let's try to calculate this for this signal, complex formula. A question that I was waiting for you guys to ask me was, you said this is good for any signal, but there is a period in it. So what do we do with that? In all the formulations there is a period too. So we said that this is good for any kind of signal. So what do we define as period? Any idea? It's much simpler than now you're thinking about something very complicated. The thing is, well, using Fourier transform for non-periodic signal is always an approximation. So you need to kind of decide on a period. And depending on, I'll show you this not long time from now, that depending on how long you actually choose, you include some artifacts in your analysis in your data. This is what it is. So for the purpose of this example, let's just take period to be 4 seconds. That would mean that whatever you are calculating is actually not for this signal, but for a signal which repeats itself every 4 seconds. So a lot of times you hear people zero pad their signals for more experienced among you. You add zeros here, so you increase your period to get closer to the reality, but we cannot make it infinitely long. We have to stop at some point, right? So it's always an approximation. Do you guys have a seminar today? They're not going.
No.
Okay, so we can continue finishing. So why don't you guys start and write out, see what is the omega with equal to 4 seconds, and write it down a little bit. What happened with that? So, yeah, it's a little bit painful to solve things, I guess. If you use Mathematica or Maple or symbolic MATLAB to calculate the integrals, that's fine. I write down the answer, so we'll see. Which class is this? That's interesting. So because it's 0 to 1, so I just wrote it like that. We all know how to integrate. So you get for C0, we get 75, which is pretty much the average. And that's something I want you always remember. The frequency amplitude at frequency equal to 0 is the average of the signal. So if your signal, the average is 0, you shouldn't have any component at frequency equal to 0. Whatever you see here is the DC component. That's something very important. And if n is not 0, we get something else. Yeah. It looks like that. Well, it's complex value, doesn't look anything very exciting. What I want to show you is this. Now the code is here, and Basically, I want you to go at home and check this code and make sure that you get what I'm getting. But what is important is here. We have entertainment too, so it's much more pleasant to talk about this abstract subject. So look what we see here. It's the code is in symbolic math, but you can write it however you want. All I'm plotting here are the partial sums. So here is 0, if it's not very clear. So this is the 0 axis. That's negative 20. So as you add components, so I start from just 5 components. The red is the average. So if you only have one component, it gives you the average. You are reconstructing the signal from its Fourier representation. If you only have one number, the best you can get is the average of the signal, which is not too bad, but it's very different from the pulse that I showed you. Now, as you add components to this, 5, 10, 20, you see how the amplitudes AN, here CN, is changing such that you are going to get closer and closer to the pulse that you had in the beginning. Does it make sense? That's why I wanted to show you this kind of to get a feeling for all of that. So this is called we call it the n's partial sum, because Fourier said you have to sum up infinitely large number of sinusoidals, which is not possible. We have to stop at some point. If you take n, so all you have is basically 75. So we call this Sn. I don't want to use any other summation. And all I am doing is going from negative n to positive n when n is a finite number, right? And I'm summing up the value that I got for Cn and then remember, this is the Cn, but the representation is multiplied by so these are the coefficients, but then to get back to the signal, you have to multiply the coefficient by the corresponding sinusoidal. It just looks complex, but it's just a periodic signal. And I think it's very much fun to program that and see, as the numbers grow, how it is getting closer and closer to the shape of the signal. And look where it struggles. Where does it struggle? Where does Fourier transform, Fourier series here is struggling to make the signal? It's pretty good here, right? I think here it looks pretty good. It's pretty much close to 100. It's very nice. It struggles wherever you have an abrupt change in the signal. When you start, and then when it is going from 0 to 100 volts, it is very hard to construct that. That's when you have to add a lot of sinusoidals to try to get this transition. And again, when you go back, that's where you have this struggle. So anything which is abrupt is not good for Fourier transform. If you have a signal and you have a pulse, which is just like what I showed you, just a boxcar or just a window, then you have a lot of artifacts in your, if you are using frequency domain analysis, you enter a lot of artifacts in your analysis. Okay. Any questions about this? I've really tried to minimize the amount of mathematics in that, but there is a little bit. Yes?
Sorry, I just want to make sure I'm following. Can you explain what CN is again?
Cn is the coefficient for the complex Fourier series. So here is the Fourier series. Let's go back to the previous one. So that's like a Fourier series representation of the signal. And Cn is the coefficient, and these are the different sinusoidals. So this is equivalent to what we saw before here. You know how I'm summing up different things to get the signal? So instead of having A1 and B1, I just have one C1. Instead of A2, B2, I just have one C2. So it tells you how much each component of frequency is contributing to that signal. Good? Any other questions? Don't worry about it. If you have seen this before, it may look easy. If you haven't seen, it may look complicated. Either way is fine. Yes? Okay. Now, what I want to get into is this Fourier transform of transient time signals. Transient is something which is short-lived. So it's a short signal. So how do we get there? Now, we have started with the Fourier series and then complex Fourier series. Let's write this one more time here so we can compare the notations, the forms of the formulas. So here is how the series look like, and this is how we get the coefficients. So when we have, you saw that, let's say what I showed you, there were 100 summed up. 100 is already a lot. When we have a transient time signal, we need a lot of harmonics. We need a lot of these sinusoidals to sum up. So it's much more convenient to use an integral to have a continuous function without going to the details of the mathematical derivation. So because of that, we use the integral notation, which looks like that. So we call it a Fourier transform. And I use a very big F with omega, like that. So instead of using the summation, we just say we have an integral. So all the omegas are welcome. We don't have discrete omegas. All of them can contribute. And that's the signal. And here is comparable to Cn. So the Fourier transform is actually nothing else but the coefficients of, let's say, a Fourier series. But here we are using basically everything. There is no period, it's infinite because we have a transient signal, and the notation becomes simpler. Now, if you want to get your signal back, let's say comparable to here, we use something which we call very similar to that. We call inverse Fourier transform. So we say we get back the signal by doing an inverse Fourier transform, which is also in the integral form now. And this is like here, so it will be positive. But pay attention, the integral is over d omega. So this is nothing else but transitioning from this summation to an integral, because we want to cover everything. We don't want to go from omega to omega 3 omega. It will be continuous. Very simple. And sometimes we call this, we write this so like real inverse. Sometimes we see a notation with inverse. So here it is, the Fourier transform I didn't want to start writing this down. I wanted kind of you to see a little bit of the concept, what this is about. Before we leave, just a few important properties of Fourier transform. One, there are more in the notes, so I just write the very important ones. One is what we refer to as Parseval theorem or identity. And that is that the Fourier transform preserves the energy of the signal. Another super important property for us is the fact that the Fourier transform of a derivative of a signal is I omega times the Fourier transform of the signal. Why this is important? Because from displacement to velocity to acceleration, we have to use derivative. So it says that if you know the Fourier representation of displacement, you can get it for velocity and acceleration. And the last one, which is very important, is that the Fourier transform of the convolution of two signals disregarding this factor 2 pi is the multiplication of the Fourier transforms. The convolution is a very important thing in signal processing, or generally in this field. And just that you remember what it is, it's when you slide one function over the other, and at each position you actually multiply them, get dot product. You can write it this way, or okay. There are a few other properties I have written in the notes that I won't repeat here. Now, it's actually a good place to for preparation for the next time to ask you to actually do the derivation for this problem on the next page. So I wanted you to once to derive the Fourier transform for an idealized hammer impact. Does anyone know how a hammer impact looks like if the hammer is a sphere and everything is ideal? How would the impact look like?
You have a very strong signal initially that exits off at the time.
No, the impact. Just if you impact.
Oh, like, concentric circles?
Yeah. It never happens like that in practice, but in theory, it's a half sinusoidal, so it looks like that. And how large it is depends on the size of this sphere that hits the surface. So, so before you come next time, it would be great if, or I'm asking you to derive the f omega, basically the Fourier transform for this function. It simplifies. It's not too bad. It's not too bad. If you use Maple or Mathematica or I don't know, MATLAB symbolic, you can very easily calculate it, and that's fine. I don't want you to integral, but it is fun to write down the formulas a little bit and just remember them better. I promise that there will be less formulas next time, but yeah, some of it is unavoidable. There are